you tired of fumbling around on small tactile switch keyboards that your fat fingers can't handle? Ouch! Introducing the Mega Matrix full-size keyboard that will make your fingers feel baby soft again. Oh yeah.
So this is a graphical LCD screen. It has the ability to draw pixels and to display text, and I've been using this for a while now, but I've always wanted to convert this graphical LCD screen into a terminal. Before I can make this into a terminal, I'll have to have a look at my input devices. And this is what I've got. It's called the Matrix keyboard. It's designed to have up to 64 individual buttons, and it works by closing a particular circuit every time a button is pressed. But it's just very clumsy. You can't really touch type with it. It's a bit small. And these tactile switches here, they rock around a bit and they don't sit well. So it's kind of hard to handle bouncing of the keys. So I really need an improvement. And this is it. It's a full-size Matrix keyboard. It was developed by James Elphick, who is part of the TEC-1G development team. Looking closer at the board, it has the ability to have two different type of key switches, Gatoron and Cherry keys. It has LED lights to illuminate the keys. Over here, you've got some switches to turn the LED lights on, and a special switch just for the TEC, which will display all the lights for every key, or just the hex pad lights, just like you see on the TEC. And just some power and caps lock LEDs, and the 20-pin connector, which connects directly to the TEC. It has some special keys here, like the reset key. This will just reset the CPU directly, and it has stabilizer supports for the spacebar and the shift and enter over here. On the back, to get all those LED lights on without them blowing up, we need resistors, and there are 60 SMD resistors already on the back. So the two types of key switches that are used are these two. One's a low profile Gatoron, and one's a Cherry style key switch. They actually both have different pinouts, but they can both fit perfectly well into the keyboard. And as you can see here, there's a bit of play with the switches here. Also, which comes with it, is a metal plate. This plate is designed for low profile Gatoron switches. They sit in here as so, and they click in place. And it's designed so you can remove these switches and change them over. Now I'm not going to use the plate because I've got the larger switches, but I'm going to use the plate to help align my switches. So let's start building this keyboard. The LEDs needed for this keyboard are these very small LEDs. I'm actually not sure what type of size they are, but they're specifically designed to sit under the keys on the keyboard. And when putting them in, you've got to just remember which leg is the positive and negative. Long leg positive, short leg negative. And on the PC board, it's labeled on top K for the cathode. That's the negative leg. Now I have a few different colors of these LEDs, not enough to fit all of them for the same color. And I've just come up with a quick split to split these colors in particular categories of the key function. And before soldering these LEDs in, I just like to make sure they're working. So I have this tester here. You should get one of these testers. They're not that expensive. The LED will flash showing it's working, also showing me the polarity of the LED as well. Alright, time to insert the LEDs.
Ready Z80, let's code and play with the Z80. CPU leading the way, assembly language. Come and take a stand in this 8-bit wonderland.
Alright, first LED in, now the rest of the 60. LED lights are all in, and for a sanity check, let's just make sure they all work. Yeah, great, they're bright. What about the hex pad only lights? Great, excellent.
Let's code and play with the Z80.
Next I'll install the stabilizers. I'm using these ASCII screw-in stabilizers. Inside the pack there are 11 different sizes. They slot onto the keycaps like so, clipped into the board and screwed in from underneath. Now the button will depress easily and it doesn't matter which side you press it on. Now for the key switches, to make them all line up properly, I'm going to use the template. Just place the template over the top, and I'm going to use some clamps and tape to clamp it all down. Yep, looks very straight to me. Okay, first row done. Now for the rest.
Come and take a stand in this 8-bit wonderland.
When soldering the switches that use the stabilizers, insert the keycap in first before soldering, and that way the key will be aligned with the stabilizer and it won't get stuck. Alright, all keys are in. Lastly, just need to finish off with the switches and the LEDs and resistors. And finally, just to make sure I haven't screwed anything up, and all the lights are on. Great! Now just putting the keycaps on, and in the right order hopefully. Keycaps are in, it's a great feeling keyboard. Lastly, the IDC cable, get that ready, and we're ready to go. To make the Matrix keyboard work for the monitor 3, this dip switch, position 1, needs to be switched to on. Okay, keyboard is now connected to the Matrix adapter. I've changed the dip switch over so that the monitor 3 will recognize this full Matrix keyboard as input. And let's turn the TEC on. Alright, it's fired up okay, so hopefully the hexpad keys here will be emulated on the keyboard. So let's do down arrow, that's working well, up arrow, escape, go back to data entry mode, and now I can type in some code, 3E01, yeah, this is working great. What about A, B, C, D, E, F? Okay, that's all filling out really well. What about the LED lights? Turn them on. Yep, they're working. And the lights that are lit up are just the lights which are the hexpad lights. So if I do function D, should give me a disassembly view. Yeah, this keyboard's working great. And there'll be other keys that don't work. Yep, they're not working. To test the rest of the keys out, there is a type-in program that is in the Monitor 3 guide where the Matrix keyboard will echo to the serial terminal. So I'll type this in and give that a run. Alright, the Matrix to serial program is running now. Typing characters on this keyboard should come out onto the serial terminal. Let's give that a go. Yeah, that was working great. What about backspace? Backspace working. Our return works. What about testing all the characters? Yeah, they all work. Caps lock, yeah, caps lock. The light comes on for caps lock. Turn, yeah. Pretty happy with this. Z80. Now there's some key bouncing kind of issues here. It's probably with the program, but the feel of this keyboard is really great. Let's try all the other characters out. Takes cap lock off. What about shift? Yep, the characters up the top, they're looking good too. Plus, minus, equals. And if I turn all the lights on as well, turn that switch, yep, they all come on. That gives you an indication that all these keys are active while using this program. The keyboard has a reset feature on board itself to reset the CPU. To do that, you need to press both these keys together. So 1 and 2, and the CPU will reset. Okay, keyboard's working. Now the more complicated part is actually getting the GLCD board to emulate a terminal. So let's firstly have a look how a terminal works and see if I can reverse engineer it. This is my terminal on my Mac OS X. It's also similar to CMD on Windows, and how it works if I type characters on the keyboard, they come out to the screen. Pressing the backspace key deletes them, and also if you keep pressing backspace, it stops at the start of the prompt. Hitting carriage return goes down to the next line. Obviously, hitting isn't a command that it recognizes. By hitting return, it does a carriage return and a line feed. Carriage return just means move the cursor to the start of the first column, and line feed go to the next line below. Also, if you hold a key down, they auto repeat. And if I get to the end, it should also overlap onto the other side of the screen. Yep. And by pressing backspace at the start of the screen here, should go back to the top of the first line, which it does. And lastly, if I hit Control D, which stands for end of transmission, the screen will close. The first thing I need to do is to work out a draw routine where it will draw ASCII characters or any other picture to the GLC. I already have a pixel plotting program already that can draw pixels. Here's some random pixels being plotted on the screen, so it's just a matter of collecting those together in some ordered format to represent ASCII characters. The format I came up with is similar to the BBC micro format. This is an excerpt from the How to Write Your Own Fantasy Games by Osborne Computing, and you can see here a pixel is drawn by having its bit set in the 1 byte. And this draw graphics routine can draw any size graphic from 1 pixel to 128 and 64 pixels down, which makes each row 16 bytes across and each column 64 bytes down. For the ASCII character format, I've decided to go with a 5x5 character font, which is really 6x6, as I use the rightmost and bottommost pixels as space characters to space out the characters. And so a Z would be represented like this in binary format with the bit set displaying the pixel. And having a 5x5 character font will give me a total of 21 characters across and 10 characters down. So here's my draw graphics routine, and what that does is it will draw a character or a sprite at a particular location. You can just send it the ASCII number that you want it to generate, or for custom characters, set D to 0, and then HL is the address data, and B and C are the width and the height. Essentially, this routine just loads the data up and iterates through the points. It maintains a particular cursor position, and by using various rotations, it can rotate and work out if the bit is set or not. It can also inverse the bit prior to printing, and there's 2 options: either draw the pixel at that location or clear the pixel at that location. Now, what about the font to display the ASCII characters? Well, I have a font data table lookup. And here's the font table, and I painstakingly keyed in almost 256 characters, and you can see here in the binary notation a bit set will be turned on, bit not set, no pixel drawn. And so there's a list of characters, and if you get to 32, which is space, here the ASCII, standard ASCII characters, apostrophe, hash, dollar, and keep scrolling down all the numbers, and so forth. With the Draw Picture program, I can now generate ASCII characters, and I can put them in any order or any position on the screen that I like. So after entering all those 5x5 font characters, here's the result, and I'm pretty happy with this outcome here. Some of the characters here are specially designed to do borders or shapes, and a 6x6, so they join together like you can see here, and some special characters at the start, like a little smiley face. I can also print pictures as well, or any size sprite or graphic to the screen. Small ones like this one. I can even print large pictures like this full 128x64 graphic. Now that looks a bit odd. Let's invert it, and also inverts as well. That looks better. And here's another picture that James has submitted. TEC-1G 8-bit computer. So I've got the characters. Now it's about controlling those characters on the screen in a way the terminal will operate as normal. Alright, so here's the main routine to send characters to the GLC and handle all the special control keys. So it handles carriage return, line feeds, form feed, backspace, horizontal tab, up and down keys for scrolling. The input is the ASCII character that you like to send to the screen, and if you just want to draw the cursor only, enter C = 0. So for scrolling, what I do is have a particular viewport, and I move the viewport up and down depending on which key is pressed, and the size of the scroll buffer changes depending on how much content is on the screen. With memory restrictions, I only allocate 10 lines of scroll buffer. So doing a carriage return would clear the cursor at the current position by drawing a space. It will increase the row, which sets the current cursor to down 1 row and at the start of the first column, and draws the cursor again. Doing a form feed is like doing a clear screen, that just resets the terminal. Doing a backspace will clear the current cursor, so put a space there. It will also decrease the current active cursor and then redraw the cursor one slot back, which also overwrites the previous character. A tab just increases the cursor 4 times and then draws the cursor. And lastly, if it's not a special key and it's actually an ASCII character, it just calls the draw graphic routine and increments the cursor by 1, and then falls through to the draw cursor routine, which just draws the cursor. And obviously, draw cursor has a flag. You can set the cursor on and off. So let's see that running. Alright, so I'll now start typing away on the keyboard, and what I should see is some characters being displayed, the cursor moving forward by 1 position, and the characters moving across in a sequential way. Let's try it out. A, B, C, D, E, F. That's good. Cursor's moving forward. Characters are being generated next to each other. If I hit delete, it should move the cursor back 1 and also remove the existing old cursor position. Yep, great. And if I go back to the very start, it doesn't do anything else because it's the start of the line. What about if I type in a long line? This is a long line. That goes, yep. So it goes over a couple lines. If I do backspace, when it gets to here, it should actually put the cursor back to the line above at the end of the columns. So yep, does that and deletes. When I press return, if I do test, go back, great. This looks like it's working well. We have we can try tabs. So tab test, press the tab key, it creates 4 spaces. Great. And I'm able to type fast enough. We're at caps lock and special characters. They're all working well. And lastly, we need to just test the viewport. So if I go down a few lines, let's type in some stuff here. It's scrolled upwards, so the viewport looks like it's moving. And if I hit the back arrow or page up, yep, that's moving upwards as well. And it actually just goes to the top of the the registered viewport. So if I do more than 10 lines down, it should lose that bit of information up the top. So yeah, that's working well. A terminal in the graphics LCD screen is now possible. So I hope you enjoyed this video.
But wait, there's more.
So part of the monitor 3 for the TEC-1G is Tiny Basic, and you can see there's Tiny Basic in the menu here. You just hit Tiny Basic and it runs through the FTDI output to your computer onto a terminal. Though it's great having a terminal where I can just type in some characters. Yeah, maybe I can leave messages for people hanging around. But having a terminal on the GLC opens this computer up to more powerful things. So I've integrated Tiny Basic with the new terminal. To activate the terminal in terms of the output, I need to go to Settings, toggle GLCD term. Now the cursor comes up on the screen, go back and run Tiny Basic, and there you are. Tiny Basic on the GLCD screen. So let's create my first program on the GLCD screen. So print ready Z80 20 go to 10, do a list, okay, and run. Ready Z80. Control C should end. Great. And I should be able to scroll back. Great. Yeah, it only saves up to 10 rows worth. Memory is precious on this computer. That should be enough. With Tiny Basic, you can also do some general programming. So new, whoops, nothing there. So I can do like 10 for I equals 1 to 20, 20 print I times I, and 30 next I. If I run that, look at the characters printing out. It does print characters or numbers out a bit slower, but look, for what it's worth, it's working really well. Alright, so there you have it. This is the TEC-1G mechanical matrix keyboard. It's brand new. It's designed by James, who is part of the TEC-1 development team. It's a great design, easy to use, has a full range of keys, and can be integrated into the TEC-1G. If you like to get one of these keyboards, then just have a look at a link below. So on that note, thanks for watching, and bye for now.
Oh yeah.